Okay, so impedance matching, as we have seen in S parameters, impedance matching plays a very major role. And always you cannot expect the source impedance to be 50 ohms, the load impedance to be 50 ohms. They are subject to change. Only the transmission line will have an impedance of 50 ohms. You cannot expect ZS to be 50 ohms and ZL to be 50 ohms at all frequencies. So if they are not having 50 ohms at all frequencies, maximum power transfer will not take place. So what I will do, I will design matching networks at the input side and output side so that these matching networks will ensure maximum power transfer to whatever impedance your ZS or ZL is going to have. So circuits at low frequencies, they don't suffer with the problem of maximum power transfer because it is maximum met in the low frequencies. But in RF circuit design, the impedance matching is the foremost condition. So without impedance matching, I cannot design any RF circuit. Okay, so these impedance matching networks play a very prominent role in RF domain. So we are giving so much importance to impedance matching. So a simple example is what is where is impedance matching required? So in an RF transmitter. So assume that this load is going to be your antenna. So I'm going the antenna impedance will be very small, but your transmission line impedance is 50 ohms. So I have to match 50 ohms to the antenna. If I connect it directly, there will be severe loss of power because the impedance are not perfectly matched. But if I include some network between the source and the load, which can transform the impedance from the Z into RL, then I can say maximum power is going to be transferred. This is a simple example of RF transmitter. So you can see here two possible impedance matching networks are given. One is L1 in shunt with the capacitance C1, or it is going to be L1. I am converting this capacitance resistance into series. It is going to be L1 C1 in series with your RS. Okay, so two possible very basic matching networks is given here. So when I cannot use only inductor or only capacitor. So I am inserting a capacitor. So to cancel out the capacitive reactance, I'm introducing an equivalent inductance L1. Okay, so that finally at the end, there is no change in the circuit parameters. So when you write from the circuit, when you find what is Z in, you apply the impedance of inductor is j omega L1, the impedance of capacitance is 1 by j omega C1. If you find out, you can find this expression Z in of j omega equal to this one. So when you take the real part, you will get this one, and you know the quality factor is omega C1 RL. So you can write RL divided by 1 plus QP square. So you can see how the impedance is getting transmitted, how the impedance is getting transformed. So RL is divided by 1 plus QP square. So I can say the value of RL will get divided. On setting, when you set the imaginary term to 0, you will get the value of L1. So again, convert that into QP square. You can write L1 is approximately RL square C1 by 1 plus QP square. Or if you assume that QP is a very large number, okay, when QP is going to be very large, I can approximate the equation to that L1 equal to 1 by C1 omega square. So in order to transform a resistance to higher value, the capacitive network shown in the figure can be used. You see here the QP value is very large, so L1, C1 values will also be very small because L1 is 1 by QP square. So when QP is very large, L1 and C1 values will tend to reduce.